So here are some graphs of some different oscillators with different amounts of friction, what I'll refer to as damping. So graph 1, the red line here, the red line maintains a constant amplitude. The amplitude stays the same. So this would be an oscillator with no friction, no damping. The green line then represents an oscillator that has some damping. Notice what happens. The amplitude gets smaller and smaller and smaller as we go along. Likewise, the yellow line would be an oscillator with even more damping. It damps even faster. The amplitude gets smaller faster. Line 1 is an oscillator with no damping, an undamped oscillator. Oscillators 2 and 3 with a relatively small amount of damping are called underdamped oscillators. Now, we know they're underdamped because they still oscillate. They're still going up and down and up and down. Even though the amplitude is decreasing, they are still oscillating. Still oscillating is a sign that it is underdamped as long as the amplitude is decreasing. Now, what if we increase the amount of damping even more? What do we get? If we increase the damping even more, we'll get a plot that looks like the blue one, number 4 here, number 4. What happens is it doesn't oscillate anymore. There is no oscillation. Imagine taking an oscillator on a spring and submerging it into a very viscous fluid, for example, and you let it go and it comes back up, but it doesn't oscillate at all. It just comes back up to equilibrium. If you were to make that fluid even more viscous, we would get something that looked like the purple line number 5, where the oscillator very, very slowly returned to equilibrium. Number 5 we refer to as overdamped, something where there's got a lot of damping. Now, number 4, there is a particular amount of damping that will actually bring the oscillator back to equilibrium in the shortest amount of time. If you have too little damping, it oscillates up and down, underdamped. If you've got too much damping, well, too little, too much is relative. If it's underdamped, it oscillates up and down. If it's overdamped, it very slowly returns to equilibrium. But right in the middle, so to speak, there's an amount of damping that is represented by curve 4 that we call critically damped. There's no oscillation, but it returns to equilibrium in the shortest amount of time possible. This is a very, very important situation that is often used for certain circumstances. So let's imagine you had a door that you could push open and you wanted it to close. You don't want to just push the door open and just have it stay open. You don't want, say, warm air getting out of your house, say, in the wintertime, or you don't want warm air coming into the house in the summertime if you're air conditioning your house or something like that. So you want to put some kind of spring on the door to bring it back closed. So you push it open, the spring brings it back closed. Now, if there's no kind of damping in the spring, you push it open and the door slams shut. So you want to put some kind of damping in the spring to slow down that motion. Now, if you underdamp it, if you put very little damping and you push it open, it will slam shut because the door is going to want to, say, oscillate back and forth. So with too little damping, it slams shut. If there's too much damping, you push it open and it very, very slowly comes back to equilibrium. It won't slam, but it stays open for a long time. Now, if you could arrange for the damping on the spring to be critically damped, you'd push it open and it would come back quickly, but not slam and not stay open for a long time. So in that case, having the door critically damped would be very advantageous to minimize the amount of air circulation from the inside and the outside. Okay, so great. That's just one example of where you might want to make something critically damped. For any real oscillator, we know that there's going to be some damping, whether it's underdamped, overdamped, critically damped, so that if we start an oscillator moving, eventually because of the damping, it's going to stop moving. Well, what if for some reason you want the oscillator to keep moving? maybe you want the motion to continue for some extended period of time. How do you do that? Well, you have to push the oscillator. For example, you have to apply a forcing function. Now, what kind of a forcing function would you apply? Would you apply a constant force or what? Well, I think the simplest example and my favorite that I always use as an example in class is imagine you have a child in a swing and the child wants to swing. They want to keep swinging. They don't want to just be pushed once and stop. They want to keep swinging. So how do you push a child in a swing? You push the child, they come back, you push them again, they come back. So at what frequency do you apply your force? Do you push them like this? Well, no, that would be too fast. That frequency is too high. Do you push them very slowly like this? You push them this way, and then you push them back this way? No, that frequency is too slow. What you do, like I said, you push them, they swing forward, they come back, you push them again, they swing forward, they come back. You match your pushing function frequency to the natural frequency of the oscillator, child on a swing. You match your frequency to their frequency. This is a very, very important and a very, very general result that comes about in all sorts of different situations. This is a result of what is called resonance. Now, let me put up a kind of a textbook definition of resonance, and then we'll take a look at a very, very important example. Resonance is the condition in which a time-dependent force can transmit large amounts of energy to an oscillating object, leading to a large amplitude motion. In the absence of damping, resonance occurs when the frequency of the force matches a natural frequency at which the object will oscillate. So, very much like pushing the child on a swing, what frequency do you push? What is the frequency of your time-dependent force? Well, a child in a swing does not have a lot of damping, and so you match your frequency to the natural frequency of the child in the swing. But I want to point out something here, which is that it matches a natural frequency of the object, not necessarily the only natural frequency. Some systems can have many natural frequencies, as this example that I'm going to mention shows. I would like to direct you to a really, really wonderful website. It's called infocobuild.com. They've got a lot of great educational things there. If you go under free education and then learn through videos and choose physics, and then under physics choose the mechanical universe and beyond. This is a set of lectures that were put out by Caltech, and they're absolutely wonderful. They are more at the calculus level course, so they're not quite the same level that we are covering, but they've got a lot of material in there that's absolutely fantastic for us. I would like to draw your attention to lecture number 17 on resonance. About 18 and a half minutes into it, they start talking about what I'm referring to, and that is the Tacoma Narrows Bridge. If you get a chance, please watch that. It is really a fantastic example of resonance and how it can be dangerous, so to speak. Okay, so try and watch that as soon as you get a chance. Resonance is a very, very important phenomenon in many, many different kinds of situations. Physical situations like the Tacoma Narrows Bridge, a child on a swing, also many other kinds of things. Electrical situations like in electrical circuits, things like that. All sorts of different kinds of situations. What I'd like to do now is go in a slightly different direction, and I want to talk about something that is actually very similar to Hooke's law, elastic deformation. Let's imagine that we've got, say, a rod, a cylindrical rod, maybe something like this, for example. Here is an aluminum rod. Let's imagine it's got some initial length L0 and some cross-sectional area A. In other words, if you were to cut across the rod and look at the area, in other words, here, A is the cross-sectional area. What's the area if you were to cut across the object? Now, let's imagine we were to apply a force on one end of this. So let's imagine that one end is kind of held fixed, so it's not going to move. attached to a wall or something like that. And then we apply a force to the other end. We pull the other end. Well, that end is going to stretch. The rod itself is going to stretch some certain amount. Let's imagine that it stretches some amount, we'll call it delta L. So what kinds of things will affect delta L? How much this thing is going to stretch? Well, we can imagine the initial length will affect delta L. If we had a rod twice as long and each length stretched an amount delta L because of the force F, then the whole thing would stretch twice as much than if it were the same original length. In other words, if it were 1 meter long, the rod would stretch a certain amount, but if it were 2 meters long, it would stretch twice as much. In other words, delta L is proportional to the initial length. Now, what about the area? Well, the more area it has, say the stronger the material would be, if we had twice as much area, we would have to apply twice the force to get it to stretch an amount delta L. So delta L is going to be inversely proportional to the area. 1 over the area. Great. Now, what about the force? If we apply more force, we expect to get more stretch. We might not say that the amount of stretching is exactly proportional to F, because if we pull very, very hard, we might get something that is not exactly a linear relationship. But for small values of F that aren't going to distort it too much, we would expect then delta L to be proportional to F. So we'll say that for delta L that has a small enough force, delta L will be proportional to the force. Okay, there we go. Great. Now, I'm actually going to write, oh, and then, well, one more thing, obviously. The material, the kind of material that the object is made of. Very weak, soft material, like maybe something like rubber or something like that, you'd be able to stretch a lot. You can imagine stretching a rubber band. It's not hard to stretch a rubber band. Something stronger, like a metal or like aluminum, it would be very, very hard to stretch this aluminum rod. So the material of which the rod is made is going to affect how much it stretches. So I'll just write that somehow as depending on the material. And it turns out, actually, that's all it depends on. When we include the material, that basically includes everything else other than the physical size of the rod itself. Okay, I'm just going to rearrange this. I'm going to leave the F over A on one side. I'm going to bring the material and the L naught over to on the other side, and we're going to write this as an equality. Here we go. So we have F over A equals delta L over L naught, and the dependence on the material I've put in here as this quantity Y. The left side, this is what we call the stress. The stress that's being applied to the rod. The delta L over L naught, this is what we call the strain. How does the rod respond to that stress? And then Y, that depends on the material, this is what we call Young's modulus. So if you want to apply this to a particular material, you can usually look up in a textbook or something like that, and they'll have a list of values for Young's modulus, and you can put those in the numbers. Put that in with the numbers in the equation. I'll give you a value, and let's stick some numbers in here. Okay, so let's try this problem. Let's imagine we have a tungsten wire that is 1 meter long and 0.1 millimeters in diameter, so a very, very thin wire, hanging from the ceiling. Initially it's hanging just by itself, but then we put a 1 kilogram mass at the bottom, so it's suspending a 1 kilogram mass. How much does it stretch when we apply this mass hanging at the bottom? I'll let you know that the Young's modulus for tungsten is 3.6 times 10 to the 11th Newton per square meter. So we can rearrange our equation, and we'll look at it like this. Delta L is F over A, the stress, then times L, so we bring the L up, divide by the Y, so we have L over Y. So the force, that is going to be the weight of the 1 kilogram mass. In other words, 1 kilogram times 9.8 meters per second squared. The cross-sectional area, assuming this is a cylinder, we cut it across, the shape will be a circle. The diameter is 0.1 millimeters, the radius will be 0.05 millimeters, so the area will be pi r squared, 0.05 times 10 to the minus 3 meters squared. The original length, the unstretched length, 1 meter, Young's modulus, 3.6 times 10 to the 11th Newton per meter squared. Multiply that out and we get delta L is 3.5 times 10 to the minus 3 meters. In other words, 3.5 millimeters. It's going to stretch 3.5 millimeters. Very, very good. Now, just as an aside, for certain types of materials, many materials have a different modulus when you try and stretch it as when you try to compress it. They're very, very different. But for metals, often you'll get a very similar value if you try to stretch it as if you try to compress it. So it takes as much force to stretch this 1 millimeter as it would to compress it 1 millimeter, or a small amount. Anyways, so we'll come back to that later on when we start looking at temperature dependence of objects. All right, very, very good. That is all for this lecture. We'll see you next time.